All right, welcome. This is Chapter 5's introduction. We're going to talk about Section 5.1 and 5.2. So let's dive into it. Chapter 5 is the conics section. So 5 is all about conics. And what conics are, let me see, I don't think yeah, they do. Yeah, all right, perfect. So conics are shapes that we can get by taking a couple of cones. Oh, look at that. You can't see what I'm doing again. Yoink, yoink. All right. There we go. So if we take a couple of cones over here, and the very first thing that we would talk about is if you just take a plane and slice it like this picture does, then you get a circle, right? You can slice these in different angles. If you slice this at such an angle that you receive this shape is called an ellipse. And if you take that plane and tilt it just right, you'll get this, right? You'll only slice through one of those parabolas, and in this case, that ends up being, or you'll only slice through one of those cones, and that creates a parabola. So that's this guy, parabola. And then if you keep tilting it more and more, you're going to end up going through both of those cones. And when you do that, you end up with the intersection of that plane and those cones here and there ends up being hyperbola. So those are what those shapes are. In section 5.1, we're essentially just going to be kind of talking about them in general. And then 5.2, 3, 4, and 5, we'll go through them in detail, starting with circles and then parabolas and then ellipses and hyperbolas. So that's kind of the plan of attack here. So that's the general gist of it. Is we have these two conic sections that are tip to tip, and it depends on how you slice it with the plane as to what conic section you end up with. And then we have some something called a degenerate conic as well. And so if I take those two cones and I take the plane and intersect them where the two tips meet, I'm just going to get 1 point. So that's why it's a degenerate conic. It's not really, I mean, it is a conic, but it's not really something we care about so much. But it is something that when we're dealing with these, your conic section can kind of collapse into just a single point, right? So a single point is a degenerate conic. But if you take that conics or that line and intersect just at the very edges of those cones. So we're at the very kind of back edge of this cone back here. We intersect on that edge, and then in the front here we intersect right there just on the very edge. We create a line. And so a line is a degenerate conic in that it comes from a conic section, but isn't really interesting to talk about as a conic itself. And then the last one, oops, that's not helpful. Let me try that again. The last degenerate conic would be intersecting lines. By having just that plane slice through both of them, and you end up getting just two lines that intersect each other, right? So those are our degenerate conics. We're not going to talk about them in great detail, but they are notable, and boom, they've been noted, right? And that's it. That's really it for 5.1 is those things. I got rid of my other pictures. Let me snag them. Is that a circle is created from one special slice of the conic. An ellipse is another particular slice of the conic. A parabola, okay. I don't know why you gotta mess with my zoom all the time. Is another slice of that conic, and then the last is the hyperbola. So we have those four conics that we'll talk about, those guys up in the top, and then the degenerate conics that are not stuff that we care about too much. Right. Okay. So without further ado, that was a quick section because that's literally it. Look at that, it's nifty. The next section jumps straight into it. Let's talk about circles. Okay, so there's no way in hell I'm ever going to draw a circle. It's lumpy, but here we go. Let's just steal one. There's a circle, and I just drew on it. There's a circle, right? We all know what a circle is. It's that. But the mathematical definition of a circle is this. A circle with a center at the point HK. So the x value of h and the y value of k as an ordered pair is the center of our circle, with a radius r, and that r has to be greater than 0. R could be 0 itself, but if that is the case, you have a point and nothing else. But if r is negative, it doesn't really make sense. So we, just to avoid having to define anything weird like that, we're just going to say r has to be greater than 0. But if this is the case, we have a circle with a center at HK and a radius of R0. That is the set of points, set of x and y values, points, right? Points in a two-dimensional system, whose distance to the point is, to the point here, to HK is the value R, right? That's really it, right? If you come and grab this point right here, it's on the circle. The distance it is from that point is R. The distance this point is from that point is R. The distance of any point on this circle, they're all are units away. That's the definition of a circle, is a collection of all of the points are units away from that center point of HK. Now, we can use the distance formula distance. I'll learn how to spell someday. The distance, I want a D there. The distance D between, let's say 2 points. Let's call that X, Y, and let's call it point. So I'm going to call it X1 and Y1 and X2 and Y2. This is a way of just denoting point 1 has X1 and Y1 values. Point 2 has X2, Y2 values. They're just general values. But the distance between these two is given by distance is equal to the square root of X2 minus X1 squared, and then plus Y2 minus Y1 squared. Right? And so yeah, this is my just general distance, but if I'm saying, well, let's choose a particular point, let's let X1 and Y1, instead of those generic points, let's say that they're H and K, that point that we're interested, the center of the circle, right? And then instead of, since I no longer have two generic bits, I'm just going to replace X2 and Y2 with a generic X and Y, where X is free to change, Y is free to change. And then I'm interested in having them R units away. And if I replace all of those things in here, the distance is now R. And my points are now, well, X2 is just being replaced with a generic X. X1 is this particular H value. And then if I go Y2 is being replaced with a generic Y minus Y1, which is being replaced with K. And I square root it. But if I come through and say, I really don't like that square root, so I'm going to take the right-hand side, square it, take the left-hand side, square it. I can clean this up just a teeny bit, and I get this formula here, R squared equals X minus H squared plus Y minus K squared. Right? And I built this distance equation into the distance between X, Y, and HK is R. And so this is equivalent to that. And this is the standard form of a circle. Standard form of the equation of a circle. So that is what this section is all about. So we'll often see it as the R on the right-hand side. It doesn't matter, it's the same thing, but you'll sometimes see it the way I've written it, and sometimes you'll see it as X minus H squared plus Y minus K squared equals R squared is a circle centered at the point HK with a radius of R. Okay. So in a circle, we can create the line or the equation of a circle given some values. What is the equation of a circle? with radius 4, centered at the point 2, -7. Well, I just plug stuff in. This 2, -7 is my HK value. So that tells me H is equal to 2, K is a -7, R is 4. So I just plug those three values into this formula. X minus H, which is 2 squared, plus Y minus K, but minus a negative goes plus, so that's Y plus 7 squared, equals R squared, so that's 4 squared, so 16, because 4 squared. And that's it. That's my standard form of that equation. Done. Right. So if we're given an equation and we're asked to find the center, the HK, and the radius, then all I have to do is grab these values. This is X minus H. So if it's a plus in there, that means this is X minus a negative number. So that means H is -3. So my center is at -3 and 4, right? So it's always the opposite of these signs in here. -3, +4. And my center, my radius is the square root of this value, right? So R squared is 36. So R is the square root of that, and I'm only interested in the positive root of that because the negative one doesn't make sense. And so then the radius here is 6. So this equation is the equation of a circle centered at -3, 4, and it has a radius of 6. All right. Excuse me. We'll want to be able to write the equation of a circle given a graph. What is the standard form of the graphed circle here? So I know my center is right here at -2, 1. So my H is -2. K is 1. My distance is just how far away I am from this point to any others, and I have 4 to choose from that are given to me here. So if I look at my X values between, let's say, the center and this point here, I can see that I go two spaces away. So my radius is 2. And therefore, my equation should just be X minus H, or X minus -2 is X plus 2 squared, plus Y minus K, so Y minus 1 squared, equals R squared, 2 squared, which is 4. And that's the equation of this line. Okay. So here we're going to be asked to write an equation that's given to us as a standard form of a circle. So let's say we have 3x squared minus 6x plus 3y squared plus 4y minus 4 equals 0. And this is why standard form is nice, is because when I look at this, I don't really know what I'm looking at. I do after many, many years of playing with these, of course, but it's hard to determine just from looking at this if it is going to end up being a circle. And we'll see that when we start playing with ellipses and parabolas and hyperbole, that it's much nicer to see things in standard form. So what I'm going to have to do is take my x terms, these guys right here, and complete the square. And if you haven't guessed it already, guess what I'm going to have to do with my y terms? These guys, I will also have to complete the square. So if you didn't like completing the square back in our previous section, you're going to double hate this because you're going to have to do it with both variables. So you may as well learn to love it, embrace it, print it out on a piece of paper and sleep with it at night because it's not going away. So I'll just treat each of these by themselves, and I'm going to take this 4 and just kind of shove it out of my way. Because I have an equation, I can do that. So I'll rewrite this as 3x squared, but I'm going to factor out of this guy. I'm going to take that first coefficient, factor it out to make completing the square easier. So I've got a 3 times my x squared minus 2x. I'm going to leave myself some space. Plus, I'll do the same thing for my y, 3. I've got y squared plus, this one's not pleasant. That becomes 4/3. That's going to be an issue. And then I've shoved my 4 off to the other side, right? So in the x, it's not the most difficult thing. My middle term coefficient is -2. Half of -2 is -1. And if I square -1, that's 1. So I'm going to add 1 here. And instead of subtracting 1 inside there, right, what I'm going to do is I've really added 3 to the left-hand side because this 1 is in parentheses with a 3 acting on it. So if I were to distribute that through, I really get a 3. So if I've added 3 to the left-hand side, I'm going to add 3 to the right-hand side. Right? And I'm still in balance. I've added the same thing to the left that I have to the right. On my y terms, these guys are a little bit less fun. But if I take this 4/3 and divide it by 2, that's the same as multiplying it by 1/2. Then I get 2/3. And if I square that 2/3, I get 4/9. So that's what I have to add in here, plus 4/9. But again, I'm not adding 4/9 to the left-hand side. I'm adding 4/9 inside that parentheses. That parentheses, of course, has a 3 acting on it. So if I distribute that 3 through, that 4/9 is really worth 4/9 multiplied by 3, which I would then say is 4/3. So I've added 4/9 in the parentheses, but to the left-hand side in total, what I've added is 4/3. And so I'm going to add 4/3 to the right-hand side as well. Okay. If you don't like this method, you can also, instead of doing this inside the parentheses, I could add 4/9 and then subtract 4/9 and then distribute the 3 to that 4/9 to get it out of the parentheses and move it over. But it's going to be 4/3. Right? Okay. I'm going to clean it up a little bit. On the left, this whole thing, that whole factor right there is a perfect square. I designed it to be. So I've got that 3 still hanging out in front, but this ends up being x minus 1 squared, which is perfect. That's what I want, is that x minus 1 squared for the circle. The other guy, this other term over here, is also 3 multiplied by a perfect square. That perfect square was y plus 2/3. It's always that whatever you took this middle term and divided it by 2, that's going to be what goes in there. Squared, and then equals, on the right hand side I have 4 plus 3 plus 4/3. So if I turn those all into all into thirds, I'm going to get 12 over 3 plus 9 over 3 plus 4 over 3. So 25 over 3. Right. But notice I'm not quite done, because in the standard form of the equation, right up here, there's no numbers in front of these guys. And so I want to divide out any numbers that are in front of there. And luckily for me, do you do that? They both have a 3. So I'm going to divide everything, the left-hand side by 3, the right-hand side by 3. And so I divide by 3, divide this whole term by 3, and then I'll multiply this side by 1 over 3. And so the 3 cancels, the 3 cancels. This becomes x minus 1 squared plus y plus 2/3 squared equals 25 over 9. Excuse me. And so I have some information about this circle. This is a circle of radius, the square root. So this 25 over 9 is r squared. So r is the positive square root of 25 over 9, which is 5 over 3. So I have a radius of 5/3 and is centered at 1, negative 2/3. And if I wanted to, I could draw this. My center is at 1 and negative 2/3, so like right there ish, right? I have a radius of 5/3, which is like 1 and 2/3, so 1 and 2/3 would be there, right? And then 1 and 2/3 down would be like right about there. And then 1 and 2/3 to the right would be there. 1 and 2/3 to the left would be there. I have no prayer, no chance in the God's green earth to ever make this a good looking circle, unless I zoom into ridiculous values. Oh, look at that. Oh, it looks ugly. And it's uglier. But whatever. That's my circle. And it's a beautiful circle, and I don't care what you say about it. Just kidding. It's ugly. All right. That's our circle. There we go. All right. Let's do this example from the book. This drives me crazy. This stupid crap. This. All right, write the standard equation of the circle that has -1, 3, and 2, 4 as the endpoints of a diameter. So what that means is I have, let me grab this picture again. It's not this circle, we're just looking at a circle for a moment, but a diameter is just some line that goes from one point through a straight line that goes through the center and then off to the other side, right? So what that means is that this center, the center of the circle, is the center of your diameter. And it's the center of every diameter. Okay? Because if your line doesn't go through the center, it's not a diameter. If I have a line that goes from here to there, it doesn't go through the center, this is not a diameter. It's a secant line, but we're not interested in that. It's a diameter, so we know that it goes through the center. So I can figure out the center or the midpoint of these two. And we're going to recall the midpoint formula. The midpoint formula here is x1 plus x2 over 2. It's just the averages of the x values as your h value, and your y2 or y1, doesn't matter, so plus y2 over 2. That's your midpoint. So if I figure that out, I know the center, and then I know one of my points, so I can figure out the rest of it. Let's figure out our midpoint here. X1, it doesn't matter which one of these is X1 and Y1 and which one is X2 and Y2. So I'll just call one X1, Y1, X2, Y2, and plug those values in. So that's -1 plus 3 over 2, comma 3 plus 4 over 2, or 2 over 2, comma 7 over 2, or 1 comma 7 over 2. So I know my center now, right? And I can figure out the radius as well, because the radius is just the distance between any point, and I have 2 to choose from. But it's the distance from either one of those points to my center, right? And so I can figure, oh, I made a mistake. And that mistake is that value right there. These should be the x value. So -1 is my x1 value. 2 should be my x2 value. So that should be 1 over 2. And so I should have 1 over 2 here. My apologies. But I can find the distance now, and I'm going to use probably this point here because it's nicer. I don't, for no reason, doesn't matter which one I use, but I'm going to throw that into the distance formula. And so again, recall that distance formula. The distance between 2 points is x2 minus x1 squared plus y2 minus y1 squared, and then that whole thing square rooted. Or if you want, you can do the distance squared formula, but this gives us r squared, which is fine because that's what's going to go into the equation when I put it into x minus h squared plus y minus k squared equals r squared. So if I find r squared, I'm fine with that. I don't care what r is perhaps, as long as I have r squared. So I'll put those values in. I'm going to put 2, 4. I'm going to say that the point 2, 4 is x1, y1. And this center point, hk, 1/2, 7/2, is x2, y2. And if I plug this in here, then I can figure out what r squared is. x2 is 1/2 minus x1, which is 2 squared, plus y2, which is 7/2 minus y1, which is 4. And then I simplify 1/2 minus 2. If I look at 1/2, instead of minus 2, I look at 2 in the form of 4 over 2. I get negative 3/2. So this is negative 3/2 squared. Plus, and if I look at 7/2 minus 4, but instead of 4, I'm going to look at it as 8/2. Still 4, but it's over 2, so I can combine these. That's negative 1/2. And so r squared is negative 3/2 squared is a positive 9 over 4. 1/2, negative 1/2 squared is a positive 1 over 4. So this is 10 over 4 is my r squared, which means my r, if I really care, is the square root of that, 10 over 4, which I can then say is the square root of 10 over 2. But again, I don't really care because it's that r squared that goes into my formula. So to write the equation of the formula, I have x minus h, and h was 1/2, so minus 1/2 squared, plus y minus k, which was 7/2, equals r squared, which was 10 over 4. Not a beautiful circle because of the fractions, but much nicer to look at in this form than it is to look at it in an expanded form or otherwise. The unit circle is used quite a bit, but the unit circle is just a circle centered at the origin, so centered at 0, 0, and with a radius of 1. So what is the equation of that unit circle? Well, we just plug what we know into the x minus h squared plus y minus k squared equals r squared. But if it's centered at 0, 0, then both h and k are 0. So that's x minus 0 squared and y minus 0 squared. And I know the radius is 1, so radius is 1. That means r squared is 1. And so this equals 1. But x minus 0 is still x. And so this just simplifies to x squared. Y minus 0 is y squared. Y minus 0 is still just y. And then that's squared. So that's y squared equals 1. And so this is the equation of the unit circle. So we might be asked to find the point or points on the unit circle that have a y coordinate of square root of 3 over 2. So it should make sense if I grab this graph here, slap it down here. We're talking about a circle. I don't really want that. I just grabbed that in the center part of that thing. We're just talking about this circle that goes around. It's 1 unit away in every direction. So they're centered at the origin. So it just looks like this. All right. Square root of 3 is less than 2, but more than 1. So square root of 3 over 2 is more than a half, but less than 1. So y coordinate of that is somewhere like probably right here. So let's just say that this is the square root of 3 over 2, right there. And as you can see, for that y value, there should be 2 x values that give you that y coordinate, right? So how do I find what those are? Well, in that equation that we just created, I'm going to plug in root 3 over 2 in for y and then solve for x. So that is, I have x squared plus this y value of square root of 3 over 2, all squared, equals 1. So that is x squared plus the square root of 3 squared just turns into 3. I have to square the denominator, so that becomes 4. And now I can solve for x squared. I'm going to subtract 3/4 from both sides. 1 minus 3/4 is, of course, 1/4. And as this, when I have x squared equals something that I take the square root, I have to consider that there's going to be a positive and a negative root. So that's positive and negative of the square root of 1/4. But I can take the square root of 1, and I can take the square root of 4. And so I get negative and positive, a positive and negative 1/2. So then I should have 2 points. Those points are 1/2, comma, square root of 3 over 2, and negative 1/2, comma, square root of 3 over 2. And that's really it. Circles are the easiest of the conic section. The biggest, I think, concern is the completing the squares, because you're going to have to do 2 squares on each. So let's grab this guy here, and I'll just do one more of those as an example. So there I've got example number 22. The first thing I want to do with this guy, it's got my x squareds and y squareds written. I want to just write this as x's on one side, not really in one side, but clumped up on the left. So I'll write x squared plus 12x, and then leave myself some room, and then write plus y squared minus 14y. And I'm going to get rid of this plus 21. I'm just going to move it over the other side just to get it out of my way. So there's going to be a lot of space here because I'm going to be adding and subtracting stuff in clumps and groups. But for this first part here, I'm going to take that 12, divide it by 2, and I get 6. And then I square that 6 to get 36. There's no numbers in front of my x squareds, which means this is one of the nice ones. I don't have to factor it out and then take that into consideration for what I add to the other side. I can just add 36 and add 36. And then for my other guy here, if I take negative 14 and divide it by 2, I get negative 7. But if I take that negative 7 and square it, I get 49. So I'm going to add 49, and then, of course, add 49. But again, keep an eye on these numbers, the 6 and the negative 7. They're going to come back. When I complete the square in my x's, it's going to be x plus 6 squared. And if you can't remember that, just factor the x squared plus 12x plus 36. You'll get x plus 6 squared. And when I factor my y's, it's going to be y minus, because of that, or because of that, 7 squared equals whatever all that junk on the right-hand side equals. I'm just going to cheat. So what do I have? 36 plus 49 minus 21. And it stopped doing anything. 49 plus 36 minus 21 is 64. Right. And so the information I know here is that the center of this circle is at negative 6, 7, and the radius is the square root of 64, so it's got a radius of 8. Let's look at yeah, this one. Yeah. God, why does it do that? All right, this guy. So now we've got those multipliers in front. My x squareds and my y squareds have a 4 in front of them. So I'm going to group them again. I'm going to write the x's in blue. So I've got 4x squared. But I don't have an x term. So I'm going to leave that for a minute. My y terms are going to be 4y squared minus 24y. And I'm going to subtract that 36 off to the other side. So equals minus 36, right? But I can treat this as it's like 0x if I want to think about it. And if I take 0 and divide it by 2, that's still 0. And if I square 0, that's 0. So I'm just going to add 0. I don't have to do this. Once we see what's happening here, you'll probably want to skip these steps because they turn kind of dumb. But for the y values, I'm going to factor out the 4. So I take a 4, and I get y squared minus 6y. But because of this, I'm like, I couldn't still, if I had factored out my 4 in my x's, it wouldn't have changed what I'd done. So this is just 4x squared over here, and that is my completed square. That's x minus 0 squared, if you want to look at it that way. You don't need to, though. You can just write it as x squared. Then here, I'm going to take half of 6, which is 3. Negative 6 divided by 2 is negative 3. And square that, and I get a positive 9. So I will add 9 here. But if I'm adding 9 here, that's 9 times 4 is 36 that I have to add to the other side. So in the end here, I've got 4x squared plus 4 times y minus 3 squared. But on the right-hand side, I get 0. This is still a circle, but it's a stupid one. What it really is a degenerate circle, a degenerate conic section where there's only one point that solves this, right? And so that point here and that point is at when x is 0 and y is 3. That's it, because that is the center. So that center is the only point because that's the only point that has a distance of 0 from that center point, right? So that's what a degenerate looks like in algebraic play. But know how to do your completing your squares because they're going to be here for the rest of this chapter. So anyway, that's it for this section. Thanks for watching, and thanks for hanging through this week, and I'll see you guys next Tuesday.